All right, section 3.4, finally we get to graph these polynomials. It's finally going to all start to come together like I keep saying. All right, so just to make sure that we are good with the terminology, here's an example of a polynomial. You have it in order of descending powers of the variable. So, you've got the highest exponent here, and then it goes all the way down to the constant at the end. So when you have them in that order, then the first term is the leading term, and that coefficient is your leading coefficient, and then that highest exponent is the degree. Okay, so right here, everything's already in order, so the leading term in that case would be 2.4 x to the third, and then the leading coefficient is 2.4, and the degree is 3. Okay. All right, and for this one right here, if you wanted to put that in the proper order, it would be x plus 12. And so the leading term then would be x. And the leading coefficient would be 1, and the degree would also be 1. All right. Now, the reason why that information is important is so that we can use it to determine the end behavior of the graph. So that's a fancy way of saying which direction are the arrows pointing on the graph, okay? So if the degree is even, both of the arrows will be pointing in the same direction. Okay, so just like with, the x squared parabola, if you think about that with the quadratic function, both arrows are always pointing the same direction, whether it's both up or both down. And if your leading coefficient is positive, it's both up. If your leading coefficient is negative, it's both down. Okay, so relate that to the quadratic function that you're already a little bit more familiar with to help you remember that. Okay, now then if you recall the x cubed graph, remember that kind of looks like this, right? So that's the graph for x cubed, has the arrows pointing opposite directions. Okay, so anytime the degree is odd, the arrows will be pointing opposite directions. Now if your leading coefficient is positive, then it's going to be down on the left and up on the right. So in other words, they might describe that as, it rises on the right and it falls on the left. And then if it's negative, you just flip those, okay? So let's start by just looking at this multiple choice problem to basically, or matching type problem, I should say, to match up the graph with the function. And we can do that just from the degree and the leading coefficient. Okay, so let's see. Hopefully you can read these okay. So for number 1, we have the leading coefficient is -4, and the degree is 8. All right, so that's an even degree, meaning the arrows will point the same direction, and the leading coefficient is negative, so both arrows are going to be pointing down. So that would have to be graph B right here. And then number 2, the leading coefficient is -11, and the degree is 3. So the degree is odd, which means the arrows point opposite directions, and the leading coefficient is negative, which means it's going to be the opposite of the regular x cubed function, so it's going to be up on the left and down on the right. So that would have to be graph D. Number 3, the leading coefficient is 5 and the degree is 5. So that is an odd degree, which means the arrows point opposite directions with a positive leading coefficient. So that's going to be just like the x cubed function, like that. So that would have to be graph C. Okay, and number 4, the leading coefficient is 1/2 and the degree is 6. So that's an even degree, which means the arrows point the same direction, and then a positive leading coefficient, which means that direction would be up. And that we can see that matches with graph A. Okie dokie. So let's look at some other information that we can find from these graphs. Okay, so the maximum number of turning points is equal to the degree minus 1. Okay, so that means that we can also determine the minimum degree by taking the number of turning points and adding 1. Okay, and that will give you the minimum degree. Okay, so let's see. So for graph A, it has 1, 2, 3 turning points. Okay, so those are the points where it changes direction. So that means that the minimum degree this could have is 4, just based on that. Graph B has 1, 2, 3 turning points, which means the minimum degree is 4. Graph C has 2 turning points, which means the minimum degree is 3. And then graph D, it has 0 turning points. So that doesn't really help us a whole lot. I would say then, you could say the minimum degree is 1, which would be a straight line, and we can see that it's not a straight line. And it can't be 2 because the arrows are pointing opposite ways. So I'd probably go ahead and say your minimum degree there is 3, just from all that information. All right. So this is, like I said, this is all just helping us to be able to draw graphs and maybe, do some matching with graphs on functions. And then this question, how many real zeros does each graph have? So real zeros is basically another word for x-intercepts. So we're just going to count the x-intercepts of each graph. Okay, so graph A has 3 x-intercepts. So in other words, it has 3 real zeros. Graph B has 1, 2, 3, 4. 4 real zeros. Okay. And then, and that also can help you figure out the degree. So however many real zeros, the degree has to be higher than that also. So, or it has to be greater or equal to that. Graph C only has 1 real zero. And then graph D also has 1 real zero. Okay. All right. Okay. On the next page, we will talk about multiplicities. Okay, which we talked about before, how to determine what the multiplicity is of each of your zeros. Here we're talking about why is that important. Okay, so that is important because that is going to tell us sort of what the graph is going to look like at each of those zeros, or in other words, at each of those x-intercepts. So if the multiplicity of the 0 is equal to 1, then basically it's going to look like a line. Because if you think about the degree of a line is 1, like y equals mx plus b, that's a degree of 1, so that's linear. So when you zoom in on that x-intercept, it's going to look approximately like a straight line. Then if the multiplicity of the 0 is even, then it's going to look similar to a parabola at that, when you zoom into that 0. Okay, so they might describe that as, it just touches the x-axis and then turns around and goes the other direction, or it bounces off. It hits that and it bounces off the x-axis. All right, then if you have a multiplicity that is an odd number higher than 1, so for example 3, then it's going to look similar to the x cubed function, okay? So I call that a squiggle. So when you zoom in on that, it'll look similar to an x cubed function. Okay, so we're going to go ahead and put all this knowledge together to finally make a graph. Okay. So another thing that is helpful to note is that the degree is equal to the sum of the multiplicities of the zeros. Okay, the degree is equal to the sum of the multiplicities. All right, so number 5. So if I was to ask you to identify the zeros of this polynomial, most people would say 5. And that's correct. And it has a multiplicity of 1. And -3 with a multiplicity of 1. And +1 with a multiplicity of 1. All right, but most people will forget about this guy right here. So remember, when you're finding the zeros of the polynomial, you're taking each of those factors and you're setting it equal to 0. So x squared is one of the factors. If you were to set that equal to 0 and solve for x, you would get that x is equal to 0. So you have a 0 at 0 with a multiplicity of 2. Okay, so that's one that people commonly forget about. So I want to make sure, point that out. So now, okay, so notice that this polynomial was given to us in factored form as opposed to expanded form. So that makes it just a tiny bit more complicated to find the degree. As long as you know what to do, it's easy. It's just not quite as obvious. So what you want to do is you need to add up the multiplicities to calculate the degree. Okay, so it's kind of like if you were to multiply all of this out. So you don't need to multiply it all out to know that, you'd have like an x squared times an x times an x times another x. Okay, so to get the degree, we're just going to add up all the multiplicities. So 2 plus 1 plus 1 plus 1, and that's equal to 5. So the degree is 5, which is an odd number. And the leading coefficient would be 1. So that means the degree is odd, so arrows point opposite ways, and the leading coefficient is 1, so the arrows are going to be like this. Okay. All right. Let's see. So let's go ahead and plot our zeros. So there's that one. 1, 2, 3, 4, 5. -3. and 1. Okay, so yeah, you know, it would be, in one way it would be helpful if these were like in order from smallest to largest, but they're not, they're just in this order. So just kind of pay attention to that. So you might want to go ahead and like put your, you could maybe go ahead and put your arrows on here. Okay. So all of my multiplicities are 1 except for this. Okay, so at this one, it's going to look similar to a parabola, but the rest of them are going to go straight through. Okay, so this is one of those situations where I feel like my color coding comes in really handy. Okay, so it's going to go straight through, bounce, straight through, straight through. Okay, so I'm going to go straight through, bounce, straight through, and straight through. And that also matches up with where my arrows are. And that's my graph. Now, the only thing that I don't really know exactly for sure is how big these hills and valleys are. Okay, so if we're drawing this by hand, and when I give my my paper tests, I don't really care how big you make your hills and valleys. So you could make it go up here like this, or you could make it a small one. I don't care. Whenever so. And then if it's a multiple choice or matching type deal, you won't really have to worry about that. There are some questions that they have on MyLabs Plus where they have you graph it using a graphing tool. And so in that case, what you need to do, I believe, is to find the y-intercept, which is really easy. If you have it in expanded form, your y-intercept is just your constant term here. In this case, it wouldn't really help. The y-intercept wouldn't really help because it's right here. But let's say if that wasn't there, then your y-intercept, you could just plug 0 for x. It'd be like -5 times 3 times -1, so it'd be like 15. And you'd be able to graph that y-intercept, and then it would make you a nice graph on the computer. So, alrighty. Number 6. All right, so this one is in expanded form. Okay, so that actually does give us a little bit of extra work that we have to do because we kind of have to factor it to figure out the zeros. Okay, so this is where we're going to use the possible rational zeros theorem. Okay, so the leading coefficient is 1, so that makes it easier. So now we're just going to basically write down all of the possible factors of 15. Okay, so factors of 15 would be plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. Okay. Now then to figure out so those are the possible rational zeros. So to figure out the actual rational zeros, we will do synthetic division on each one. So I always like to just start at +1. So we're looking to see if we're going to come out with a remainder of 0. And if we do come out with a remainder of 0, then I would say, okay, that one worked. It was a 0. Otherwise, I would say that didn't work. It wasn't a 0. Okay. So I'm going to start by putting +1 in the box. And if that doesn't work, I'll go to -1. And if that didn't work, I go to 3. If that didn't work, I go to -3. And I just go down the line like that. And if you do have any fraction ones, I usually prefer to just skip those. If I can, and usually I don't have to do them, but that's up to you. All right, so then my coefficients, I've got 1, 3, -13, -15. So 1, 1, 4, 4, -9, -9, and that'd be -24, which is not equal to 0. So therefore I would say, okay, 1 did not work, and I would move on to do -1. So then I would put -1 in my box. And then I've got 1, 3, -13, -15, 1, -1, 2, -2, -15, +15, and 0. So that did work. Okay. So I know that -1 is a 0 of the polynomial. So when I'm going to factor it, I can say that f of x equals x, so minus -1, which would be like x plus 1. And then this is x squared plus 2x minus 15. Oh, sorry, plus 2x. Yeah, okay. All right, and then I can just factor this to complete it. So I've got x plus 1. So two numbers that multiply to -15 and add up to +2 would be -5 and +3. Okay, and so then, so my zeros, I have, they all have multiplicities of 1. So I've got a 0 at -1. And then I have a 0 at +5 and -3. And like I said, they all have multiplicities equal to 1. All right, and we can see that our degree is equal to 3, and our leading coefficient equals +1. So that means my arrows would be like this and like that. All my multiplicities are 1, so everything's just going to go straight through. Here's my zeros. Okay, so there is my graph. All right, so like if you were having to graph this on the computer, you would know that your y-intercept is -15. So it would be way down here. I don't have enough room on this page to graph it, so it would actually be like way down here, a big woo, you know. But if you were doing this on the computer, they give you like these big graphs, so you'd be able to plot that. All right. All right, number 7. So for this one, we are going to have to factor it, but we don't even have a constant term to figure out the possible rational zeros, but we do have a GCF of x squared. That's the first thing I want to do, is factor out that GCF of x squared. So that'll be x squared times 3x squared plus 5x minus 2. And then let's go ahead and factor this. Okay, you could use the AC method. I'm going to try guess and check. I know I'd have to have 3x, x, and then let's see. So to make the 5, let's see. They're going to have to be, I think we're going to have the 2 here and the 1 here, and the plus here and the minus here. Let's see. So that would be 6x minus 1x. So yes, that's right. Okay. All right, so now it's totally factored already. And you can see that we have a 0 at 0 with multiplicity 2. Okay. And then we'll do, this one is easy. That's a 0 at -2 with a multiplicity of 1. And then I'll go ahead and do this one. 3x minus 1 equals 0. Solve it for x, so add 1 to both sides. 3x equals 1 divided by 3, so x equals 1/3. So I have a 0 at 1/3 with a multiplicity of 1 also. Okay, now let me see here. See if I can scale this out. Okay, so if I say that this is 1/3, this would be negative 1/3, negative 2/3. This would be negative 1 right here. And this would be negative 2 right here. Okay. All right, that's nice. Okay, so that way I'm spread out a little bit. All right, now let's see here. My degree, I can just look at my original here to see that my degree is 4. My leading coefficient is 3. And we can also like kind of confirm, okay, degree is 4. Would that be the same as the sum of these multiplicities? Yes, it would. Okay, so that kind of is a little confirmation there. So if the degree is even, that means both arrows point the same way. Leading coefficient is positive, so it's going to be both up. Both arrows are up. Let's see, let me do my, okay, yeah. Let me plot my, my zeros. There's that one. There's that one. And here's this one. Okay, so, okay, this is going to go straight through and then bounce and then straight through. My arrows are both up. So there we go. There's my graph. All right. Let's see. I know my camera here was going to limit me to the length of my video. I'll try to finish this problem before I have to cut off this part of the video. Okay. Let's see here. So in this case, I am going to have to find my possible rational zeros. All right, which are going to be my factors of 16. Leading coefficient's -1, so I don't have to worry about that here. So my possible rational zeros is going to be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8, and plus or minus 16. Okay, so let's go ahead and put 1 in the box. And then my coefficients, I've got -1, and then I'm going to have to put a 0 because I don't have the x squared, then 12, then 16. So -1, -1, -1, -1, 11, 11, 27. So 27 does not equal 0, so therefore 1 is not a 0. All right, so now let's move on to putting -1 in the box. -1, 0, 12, 16. -1, 1, 1, -1, 11, -11, and 5. So 5 is also not equal to 0. So -1 is also not a 0. So next I will put +2 in the box. -1, 0, 12, 16. -1, -2, -2, -4, 8, +16, +32, which doesn't equal 0. So that didn't work. So next I'm going to put -2 in the box. negative 1, 0, 12, 16, negative 1, 2, 2, negative 4, 8, negative 16, and 0. Alright, so now we know that negative 2 is a 0 of the function. So let's start writing down the factored form of the function. So f of x equals x minus negative 2, which is going to be x plus 2. And then what's left is going to be negative x squared plus 2x plus 8. Alright, and then we just need to factor this. Okay, so I would like to go ahead and factor out the negative and just put it in front of all my parentheses. So now this will be x squared minus 2x minus 8. Okay, and let's factor that. So that will be, all right, so that's going to be minus 4 plus 2. So I can see that I've got x plus 2, x plus 2. So I'm going to write that as x plus 2 squared. I've still got that there, and then I've got the x minus 4. Okay, so this is the factored form of the function right here. So now I know that the multiplicity of that 0 at negative 2 is actually 2. And then I have another 0 at 4 with a multiplicity of 1. Okay, and so I know that just from looking at here, my degree is 3, which also it lines up with the sum of these is 3, and my leading coefficient is negative 1. So opposite arrows, that's going to be up, then down. That's going to be my arrows. Alright, let's see. My zeros are at negative 2 and positive 4. Video's about to cut me off. I'm going to hurry. Okay. It's going to bounce from this one. It's going to go straight through from that one. So the arrow is up. It's bouncing. It's going straight through. Okay. Alright, I think I made it through.